Thank you for inviting me to the exploration webinar series. So I'm Avish Kumar, a third year PhD student at the James Cook University, and my presentation is on critical metal mineralization in fractionated granite systems of Herberton mineral field. In particular, I will be looking at indium mineralization. So in the photo, the township of Herberton is shown, and the region is known for polymetallic tin mineralization in Australia. I'd like to thank a Geological Survey of Queensland for financially supporting the research, and James Cook University for providing a research environment. So this is a graph of supply risk versus economic importance, and everything inside this red square is sort of considered critical. And critical metals are used in basic to technological industry, and there is a high supply risk that is mostly associated to their geological deposition. This is a very simplified map of Australia, showing the distribution of indium occurrence and mineralization, and most of the resources are the indium resources are associated to tin mineralization, except for the Broken Hill deposit, which is associated to the lead zinc system, right? And then we also have the VMS systems down in Tasmania. My study will be focused at Belgamen and Isabel in Northeast Queensland. So the geology of Herberton mineral field, the numbers 1 to 8 sort of represent indium occurrences in the region, and the study sites of Belgamen and Isabel. So the youngest volcanic unit is the Atherton basalt, followed by the Kulmun volcanic group, which consists of Slotayard Creek volcanics at the research site. And then we have the Utan supersuit, consisting of the Watson Vale granite, and then we have the Almaden supersuit, consisting of Kalunga granodiorite at research site. And then we have the older supersuit, which is the O'Brien's Creek supersuit, and that sort of hosts the tin mineralization in the Herberton mineral field. And then we have the Hodgkin's meta sediments over here. So I'd just like to use these plots to highlight what are we talking about when we sort of say fractionated granites, right? So the fractionated granites that I sample were the Herberton Hill granite and the Jumna granite, and those are the ones that actually host tin mineralization in the region. And these granites actually have a high rubidium content compared to your normal granites and granodiorites. And the other thing to notice is that the fractionated granites tend to have a fairly flat RE fractionation pattern and a very high europium anomaly. And we tend to sort of compare to your sort of normal granite and felsic units, and we tend to see this a very high negative europium anomaly in other tin fields as well. So so this is some of my results from field work at Belgamen. So in red, you can see the structures over here, and then you have the meta sediments, which is part of the Hodgkinson's formation, and that gets included by the UNA porphyry, and everything surrounding the UNA porphyry is silicified. So UNA porphyry is what hosts the tin mineralization at Belgamen. And with it also comes in a late phase of base metal mineralization. And all of that gets cross-cut by a quartz feldspar porphyry that is coming out from, is sort of placed in the Slotayard Creek volcanics relating to the Kulmun group. On top of these deposits, we have a supergene cap that normally consists of copper oxides and carbonates. Isabel deposit is primarily sort of fault hosted within the Hodgkinson's metasediments, and the mineralization is also cross-cut by a porphyry dike from the Slotayat Creek volcanics. So this cross-cutting relationship, we can use it for dating the mineralization in relative terms. So the yellow dots on this map sort of marks the my sample points, and these are the points where the granite geochemistry that I showed earlier were coming from. So looking at the tin granites, which is the Jamna granite and Herberton Hill granite, they date to about 365 to 339 million years. And then you have the Kalunga granodiorite from the Almaden supersuit, and they date to about 313 million years. And then you also have the older metasediments that at the site we dated to about the maximum depositional age to about 456 million years. And then the cross-cutting volcanics were dated to about 292 million years. Now the Una porphyry at Belgammon were dated to about 333 million years. And then the later phase, which is not mineralized, which is the Watson Vale granite, were dated to about 285 million years. So we have looked at the geochemistry of the granites and the geochronology of it. And now let's have a quick look at where actually indium sits in these deposits, right? So you have chalcopyrite and pyrrhotite that basically co-precipitated. And within the chalcopyrite and pyrrhotite, you have sphalerite as inclusions. And there are some earlier phases such as magnetite and some later phases such as arsenopyrite. So we can actually do some geochemical modeling on those phases to understand the conditions that were necessary for indium mineralization in this sort of systems. So you have EH in volts on your y-axis and pH on x-axis. So I've just zoomed in to this section the system was modeled at, and that is at 200 degrees Celsius. And the reason for using 200 degrees Celsius is because arsenopyrite is unstable above 200 degrees Celsius at roughly 1 bar. So the system is modeled in a xenothermal to epithermal system. And the hydrothermal fluids initiated mineralizing pyrrhotite and chalcopyrite in reduced conditions. And over time, as the system switched to being more reduced and slightly less acidic, that's when you start to precipitate out arsenopyrite. And we can sort of see evidence for this in the country rock, as because surrounding the massive sulfides, the chalcopyrite and pyrrhotite, you'll normally see a silicification zone, right? So we started to investigate a little bit more about the indium in this sulfides, and what we started to find is that the early cassiterite phases that were coming out more or less from the Una porphyry were getting altered to sternite. And after analyzing a couple of sternite phases, we tend to find two groups of sternites. One was casterite, which is a zinc-rich end member, and the other one is ferrocasterite, which is an iron-rich end member. And what we find basically is that the casterite tends to have like about 6 to 10 weight% of indium in it, compared to ferrocasterite, which would have about 1 weight% of indium in it. And the host minerals, such as the chalcopyrite, can have about 4,000 ppm of indium in it. So combining everything together, so this is a sort of a mineral paragenesis sequence adapted from Kelly and Tanner. And what we see is that like at higher temperatures, tin starts to precipitate out, and you can see I've placed down Yambo's ages and mineralization stages as well from his paper. And after the tin phase, that's when you start to precipitate out the critical metals with the base metal mineralization. And that's when the moly, the tungsten comes out, and then indium sort of comes out at around 200 to 300 degrees Celsius. We know this because we know the temperatures that are normally associated to indium mineralization.
Avish, can you wrap up soon, please?
Yeah, so I'd like to finish over here with a thank you note. But before that, I'd like to highlight the solar panel. So the mineral casterite can be used for making solar panels. I guess the path to a greener economy is long, but Northeast Queensland has some of the minerals and metals in their deposit to make this a possibility. Thank you.